In this video, we're going to talk about transistors. Transistors are electronic devices that can be used as switches where you could use a small amount of current to drive a larger current to power something, let's say like a light emitting diode, or you could use them to amplify a small AC signal. We're going to talk about two types of transistors, the NPN transistors and the PNP transistor. These transistors are known as bipolar junction transistors in that they have two junctions. So here's one way to describe the NPN transistor. The first junction is right here. It's between the P and the N-type semiconductor material, and here is the second junction. So bi means two. So we have a bipolar junction transistor. The emitter and the collector of an NPN transistor are made up of the N-type semiconductor. The base is made up of the P-type semiconductor. An NPN transistor is essentially two diodes connected to each other. The diode always points towards the N-type material. So here's a typical diode, and this is the PN junction of that diode. The P-type part of the diode is known as the anode, and this is the cathode. When you connect the anode to a positive potential and the cathode to the negative potential, current will flow through the diode, and the diode will be in forward bias mode. So it's going to be active with a voltage drop of about 0.6 to 0.7 volts for a silicon diode. Now, if you reverse the polarity, let's say you connect the positive terminal of a battery to the cathode part of the diode and the negative terminal to the anode. In this case, the diode will be in reverse bias mode. It's going to be off unless you exceed the maximum reverse voltage that it can handle. So it's important to understand the terms forward bias and reverse bias because when solving problems associated with transistors, you need to know if you're dealing with the active region, the cutoff region, or the saturation region. Now let's spend a minute talking about the PNP transistor. So everything is in reverse for this particular transistor. So instead of having two N-type materials and one P-type material, we have two P-type materials and an N-type material. So the base is made up of the N-type semiconductor. The emitter and the collector is made up of a P-type material. So the equivalent symbol for the PNP transistor using diodes looks like this. Now, if you purchase, let's say, one of the small NPN or PNP transistors, they will look like this. Let's use the 2N2222 NPN transistor. This is the emitter, this is the base, and that is the collector. Now let's talk about how we can draw the electrical symbols for an NPN and a PNP transistor, especially when drawing circuits. So let's start with the NPN transistor. First, draw a circle, and then draw the base. The emitter points away from the center of the transistor. Let me use a different color to represent that. So that is the emitter. Whenever you see the arrow, that is the emitter part of the transistor. This is the base, and that is the collector. The base always is in the middle. So now for the PNP transistor, the base is going to be in the same location, but this time the emitter is going to be pointing towards the center as opposed to away from the center of the transistor. So this is the emitter, that's the collector, and this is the base. Now for an NPN transistor, the emitter is it's usually connected to the ground. For a PNP transistor, the collector is typically connected to the ground. The emitter of the PNP transistor typically goes to the positive voltage source, and the collector of the NPN transistor goes towards the positive voltage source. Now for the base of an NPN transistor also goes to the positive voltage source. But for a PNP transistor, the base goes towards the ground. Now you definitely want to connect a resistor to it because you want the base current to be very, very small. Too much base current can destroy the transistor. It can allow a large collector current to flow through it, and that could cause it to overheat, damaging the component. Now let's talk about some other things that you need to know regarding these two transistors. Current flows into the base of an NPN transistor, whereas for a PNP transistor, it flows out from the base. Keep in mind, this is opposite to the direction of electron flow. Conventional current flows from a high potential to a low potential, but electrons flow from a low potential to a high potential. So just keep that in mind. One of the many reasons why I like to use conventional current when analyzing circuits involving transistors is that the direction of the emitter arrow tells you the direction of the emitter current. The collector current flows towards the NPN transistor, and the emitter current flows away from it in the direction of the emitter arrow. Now for the PNP transistor, current is going to flow from the positive potential to ground, and so this is going to be the emitter current, and as you can see, it's in the direction of the arrow. The collector current is going to be flowing away from the PNP transistor, and the base current flows away from it. So these two transistors are completely opposite to each other. In an NPN transistor, the base current flows into the transistor or into the base terminal, whereas in a PNP transistor, it flows away from the base terminal. As you can see, the collector current flows towards the transistor in an NPN type device, but in a PNP type device, it flows away from it. But the direction of the arrow always tells you the direction of the emitter current, whether you're dealing with an NPN or a PNP transistor. So those are some basic things you want to know about these two types of transistors. But for the most part, we're going to be focusing on the NPN transistor as part of our circuit analysis. Now let's go over some formulas that you want to be familiar with when dealing with transistors. The first one is this one. The collector current is equal to beta times the base current. The base current is IB, the collector current is IC. Beta is also represented by HFE. When you're buying a transistor, look for this number, HFE, that's your beta. That's your current gain. Now, IE is the sum of IC plus IB. That's another equation that you want to write down. And if we replace IC with beta times IB, we could represent IE in terms of IB. So factoring out IB, IE is equal to IB times beta plus 1. So you want to make sure that you know these two equations. And then once you have it, you can come up with this equation if needed. So here's a problem for you. Let's say we have an NPN transistor. And let's say that this transistor has a base current of 50 microamps. And the transistor has an HFE or a beta of 200. Calculate IC and IE in this example. Calculate the collector and the emitter currents. Feel free to pause the video. So IC is going to be beta times IB. Beta is 200, and so if we multiply that by 50 microamps, 2 times 5 is 10, carry over the 3 zeros, we get 10,000 microamps. Now keep in mind 1,000 microamps is equal to 1 milliamp. So 10,000 microamps, that's 10 milliamps. So that is the collector current, is 10 milliamps. Now the emitter current is the sum of the base current plus the collector current. So the base current is 50 microamps, and then the collector current is 10,000 microamps. So the emitter current is 10,050 microamps, which is 10.05 milliamps. But you can say that's approximately 10 milliamps. So when HFE is large, let's say if it's greater than 100, IE is approximately equal to IC. 10 milliamps or 10.05 or even 10.1, that's still about 10 milliamps. So sometimes you could use this approximation to simplify calculations in the future, especially when you have difficult transistor problems that you're trying to solve. Now let's talk about some other things that you need to know with regard to NPN transistors in circuits. So that's the base, that's the collector, this is the emitter. By the way, if you're wondering how to connect the battery for this circuit, the negative terminal of the battery you want to connect to ground. The positive terminal of the battery goes towards where the plus 9 voltage or plus 9V is. So the original circuit is equivalent to this circuit with the positive terminal connected at that point. Just in case you were wondering. So this is the base resistor, RB. This is RC, the collector resistor. And this is the resistor that's associated with the emitter, RE. Now, this is going to be VE, that is the potential at point E with respect to ground. The potential at point C with respect to ground is known as VC, and the potential at point B with respect to ground is VB. So if you were to connect a multimeter to point E and the ground, the voltage that you would read is VE. VCE is the difference between potentials VC and VE. So if you connect a multimeter between points C and E, the voltage that you'll get is VCE. Now this here, if you connect a multimeter between those 2 points, that's going to be VBE. So VBE is the difference between the potential at B and the potential at E. Now, for most NPN transistors, this is going to be somewhere between 0.6 and 0.7 volts. So this value is pretty constant. Therefore, you could use it when solving circuits involving transistors. The last one you need to be familiar with is VCB. This is the difference between the potential at point C and the potential at point B. Now another one, which is quite different from the previous three, is VCC. This is the collector supply voltage. In this case, it's going to be positive 9 volts. It's basically what you see here. VEE, let me use capital E, is the emitter supply voltage. And in this example, that's the ground voltage, so that's going to be 0, which we really don't have to worry about for that circuit. Now let's talk about how the transistor can be used as a switch in circuits. So what we have here is a 12-volt battery connected to the base and the emitter of the transistor by means of a base resistor RB and a switch S1, which is currently open. The 12-volt battery is also connected to the collector and the emitter region of the transistor through RC and D1. This is going to be a green LED, a light emitting diode. Now, when the switch is open, there's no current flowing to the base. In order for the transistor to be active, VBE has to be 0.6 or greater. So right now, because there's no current flowing to the base, the transistor is off, which means that there's no current flowing from the collector to the emitter of the transistor, which means that D1, the light emitting diode, is also off. So S1 is a switch that controls a small amount of current, which will also control a larger current flowing through the LED. And that's the purpose of the transistor, at least one of its many operations. It's using a small current to control a larger current. Now let's see what's going to happen when the switch is turned on. So now let's close the switch. At this point, current will flow from the positive terminal of the battery through the base, so that's going to be IB, and then current will flow from the emitter. Now, once we get a small amount of current flowing through the base, that is, when the potential of B is 0.6 or more, the transistor will now be on. So the switch between the collector and the emitter of the transistor is now active. Thus, current is going to flow from the battery through the collector, through RC. So this is going to be IC. It's going to flow through the light emitting diode. So now this diode is on. And then to the collector, so that's IC, and then to the emitter, which will be IE. So that's how the transistor can act as a switch. You could use a small current, such as IB, to control a larger current, IC. Now let's talk about solving a circuit such as this. So let's put some numbers to this problem. Let's say that RB is 100 kilo ohms. You want a large resistor because you don't want too much current flowing to the base of this transistor. And let's set RC to 1 kilo ohm. We don't want too much current flowing to the light emitting diode, such that it burns out. Most light emitting diodes can handle about 20 to 30 milliamps of current. So a 1 kilo ohm resistor won't prevent more than 12 milliamps of current flowing through D1. If you do 12 divided by 1,000, you get 0.012 amps or 12 milliamps. So that is the maximum IC current that we can get in this circuit. It's VCC divided by RC. If we had RE, we would add that as well, but we don't have that. This is also known as the saturation current. Now for this problem, I'm going to change RC from 1 kilo ohms to 220 ohms. And we're going to say that beta is, let's make it 100. That's going to be our HFE value for the transistor. And this time I put the transistor in a circle, which is what it should be. R is for resistors, D is for diodes, in this case light emitting diode, S is for switches, and Q, that's for a transistor. So in this problem, go ahead and calculate IB, IC, and IE, and calculate the potentials at point C, B, E, as well as point D, and we'll call this point A. So go ahead and solve this problem. The first thing I would do is set the ground potential to 0. And then we could determine the potential at point B. Keep in mind VBE is between 0.6 and 0.7 volts. So we're going to say that VBE is 0.6 volts for this problem. As the base current increases, VBE increases slightly. So if the base current is very, very, very small, VBE is going to be close to 0.6 volts. If the base current is relatively large, let's say like 100 microamps or 1 milliamp, it really depends on the transistor, but if it's relatively large, VBE might be close to 0.7 volts. But for this problem, we're going to say that it's 0.6 volts to keep it simple. So that means the potential at point B is 0.6 volts. Now that we know that, we can now calculate the current flowing through RB, which is IB. The potential here is at 0.6 volts, and the potential on the other side of the resistor when S1 is closed, that's going to be the potential at point A, which is 12 volts. According to Ohm's law, in order to calculate the current flowing through a resistor, it's going to be the voltage across that resistor divided by the resistance. So in this case, IB is going to be the voltage across the resistor, which is VA minus VB. It's the difference between the potential at A and the potential at B divided by RB. And so that's going to be 12 volts minus 0.6 volts divided by 100 kilo ohms. So 11.4 volts divided by 100 kilo ohms. Now something I do want to mention is that when you divide volts by ohms, you're going to get the current in amps. If you divide volts by kilo ohms, you're going to get the current in milliamps. So 11.4 divided by 100 will give us a current value of 0.114 milliamps. So when you understand that, you don't need to convert amps into milliamps, nor do you need to convert kiloohms into ohms. So now that we have the value of IB, we can calculate the value of IC. So this is 0.114 milliamps. IC is going to be beta times IB, and beta is 100, IB is 0.114 milliamps. So multiplying it by 100, we need to move the decimal 2 units to the right. So we get a current of 11.4 milliamps for IC. So that is the current that is flowing through RC. It's 11.4 milliamps. So now that we know the current flowing through RC, we can calculate some potentials around that point. We know the potential at A is 12 volts. So using Ohm's law, we can calculate the potential at point D. So the voltage is going to equal the current times the resistance. The voltage is going to be the difference between the potentials at A and D. This is going to equal IC times RC. So rearranging the equation to calculate the potential at D is going to be the potential at A minus the voltage drop across RC, which is IC times RC. So the potential at A is 12 volts. And keep in mind, VD is going to be lower than VA because the current flows from a high potential to a low potential. So it's going to be 12 volts minus the current of, now since this is in ohms, we want this to be in amps. 11.4 milliamps. If you divide that by 1,000, you'll get the current in amps, which is 0.0114 amps, times the resistance of 220 ohms. So 12 minus 0.0114 times 220, that gives us a potential at point D, which is 9.492 volts. Now that we have the potential at point D, we can now calculate the potential at point C. Now for this, we can get an estimate because we know the voltage drop of a typical green LED. For the most part, it's approximately 2 volts. It can vary. It can be 1.8 volts. It could be 2.2. But we're going to go with an estimate of 2 volts. So that means that the potential at C will be 7.49 volts approximately. And so VCE, which is the difference between these two, that's going to be 7.49 volts as well. Ideally speaking, when creating a transistor circuit like this, especially when using it as an amplifier, you want VCE to be half of the collector supply voltage. So in this example, the collector supply voltage is 12 volts. When designing an amplifier, you want VCE to be half of that, 6 volts. This is known as midpoint bias, if you want to gain the maximum benefit of the amplifier. Now, there are 3 important regions to be familiar with when dealing with transistors. The first is the cutoff region. Next, we have the active region. And the third operating region is the saturation region. Now, during the cutoff region, the emitter has a higher potential than the base. So in this case, we could say that VB is less than VE. Or we could say that VBE is less than 0.6. If that's the case, the transistor is off. In this case, the emitter base junction is in reverse bias mode. Notice that the direction of the current is opposite to the direction of the arrow. So that's reverse bias mode. Now the potential of the collector is going to be higher than the potential of the base. So the collector base junction is also in reverse bias mode. So when those two junctions are in reverse bias mode, you're operating in the cutoff region. the transistor is off. Now let me draw a line to separate these regions. During the cutoff region, VCE is approximately equal to the collector supply voltage, and the collector current is approximately 0 amps. You might get a small collector current depending on the voltage, but if it is there, it's going to be nanoamps. It's very, very close to 0. Next, we have the active region. Now, in the active region, the potential at the base is going to be greater than the potential at the emitter. And it has to be, VBE has to be more than 0.6 volts, or it should be equal to or greater than 0.6 volts to be more specific. When that happens, the transistor is going to be in its active state, and now the base emitter junction is in forward bias mode. Now the collector still has a higher potential with respect to the base. So the collector base region is still in reverse bias mode. In forward bias mode, the current is in the direction of the diode arrow. In reverse bias mode, you can see that the current is in the opposite direction of the arrow of the diode. Now let's talk about the saturation region. In the saturation region, the potential of the base is still greater than the potential of the emitter. So VBE is still equal to or greater than 0.6 volts. So this is in forward bias mode. Now, in the saturation region, the base has a higher potential than the collector. So current is going to flow from a high potential to a low potential. So therefore, the collector base region is also in forward bias mode. Now for the cutoff region, we said that VCE is equal to the collector supply voltage VCC. In the active region, VCE is going to be between 0 and VCC, the collector supply voltage. Under saturation conditions, VCE is 0. So let's say if the collector supply voltage is 9 volts, VCE is going to be between 9 volts and 0 volts. If it equals 9 volts, it's in the cutoff region. If it equals 0, it's in the saturation region. So that's why it's important to know what the VCE value is, because by knowing it, you could determine if the transistor is operating in the cutoff region, in the active region, or in the saturation region. So VCE, knowing that value, is very important. Now the second thing you could use to determine if the transistor is operating in the cutoff, active, or saturation region is the IC value. If the IC value is close to 0, it's operating in the cutoff region. If the IC value is between 0 and its maximum value, which I'm going to call IS, that's the saturation current, then it's in the active region. The maximum IC value, or the saturation value, is going to equal the collector supply voltage divided by RC plus RE, if RE is there. If RE is not there, if there's no emitter resistor, it's just VCC over RC, assuming we don't have an LED or a light emitting diode. If there is a light emitting diode, like in the example problem that we had, the saturation current will be VCC minus the voltage drop of the diode divided by RC. We didn't have RE in that example, so we could use that to calculate the maximum saturation current. Now, in the active region, IC can be calculated by using this formula, beta times IB. This means that as beta increases, IC will increase proportionally. In the saturation region, if you increase the beta current, IC will not change. It'll be at its maximum value. So that's how you know if you're in the saturation region. If you're increasing the beta current by decreasing RB, and if you realize that IC is not going up, then the transistor is operating in the saturation region. And then you can also tell by measuring VCE. If you connect a meter between the collector and the emitter pin of the transistor, if it's approximately 0, the transistor is in saturation mode. So those are some ways in which you could determine if the transistor is in the cutoff region, the active region, or the saturation region. Now, if you want to design an amplifier, if you want to make the most ideal amplifier, you want to create a midpoint bias type amplifier. That is when VCE is 1/2 of VCC and when IC is 1/2 of the saturation current.